Now the next thing, other than a stack, is a queue. Now a queue is another data structure, but instead of last in, first out, you have first in, first out. So everybody's familiar with a queue, right? So you join from the back of the queue, you leave from the front of the queue. And the operations are called NQ and DQ. And peek is similar when we just want to see what is the head of the queue. Now, there are many examples of a queue, but when you actually need to use a queue, it's actually when first come, first serve is needed. For example, here, we say printer spooling, so meaning that you send a job to the printer, but the printer may actually, it's a mechanical device, so it may print slowly. So you can send more jobs there than you can actually print out the things. So meaning that while it's waiting for the printer to be ready, it will join a queue, and then the printer will just pick up anything that comes from the queue. You may also use it for asynchronous transmission of data. So in a way, asynchronous meaning like it's like sending messages, right? So if you take a phone call, for example, if you try to send a message through a synchronous link, then both sides, the recipient and the sender, are going to be tied up. And if one side is faster than another one, then usually they just keep waiting for the messages to come in. That is not efficient. So another way to break the dependency is to introduce a queue in the middle. So every time the sender is ready, it's going to push things into the queue. Anytime the recipient is ready, it's just going to pick up messages from the queue. And then in that way, they don't have to wait on one another. Now, 3 queue operations. The first one is to end queue. To end queue meaning that it's going to join from the tail. So if the current queue has green and orange, and QE joins later, QE joins at the tail of the queue. To peek is to look at the head, but not remove anything. To dequeue is to remove the element at the head of the queue. Now, one example of using a queue, we can use it to solve palindromes. Now, this is something that we talked about earlier when we talked about a recursion. But in this case, we can actually use a combination of a stack and a queue. Now, suppose that you have a word. Now, reading it from left to right is MADAM. Reading it from right to left is also MADAM. And that is a palindrome. So to simulate this context of like reading from the left, reading from the right, what we're going to do is to create a stack and a queue. We're going to push all the characters into the stack and into the queue. Now, by the time you push all the letters into the stack, when you pop things out, you're going to be popping the last elements first. So that is kind of like reading from right to left, because you're popping from the right all the way to the left. But if you put it into the queue, first in, first out, so the first M is going to be at the head of the queue. So as you pop and you dequeue, you just need to check whether they're equal. And if they're always equal, meaning that it's now a palindrome. So then the code for a palindrome could then be expressed in the following way. For every character you push into the stack, you unqueue it. And for as long as the stack or the queue is not empty, you take one character from the stack, you take one character from the queue, then you just need to check whether they are the same. If they are not the same, then this is false. Otherwise, then they all match, and this is a palindrome. Now, you can also implement a queue using a list. So in this case, you designate a specific location as the head. And if the head here is 0, meaning that every time we put in a new item, let's say kiwi, right? Then this item is going to join at the tail end, and that is simple because you just go right to the end, and that is O1. Now, to pick, you just take the element at 0, that is O1. But to dequeue it, now when you dequeue, it means that you take the head, and because the head is at 0, you need to shift everything up by 1. So as the shifting is n minus 1, so then this complexity is going to be O n. So here, so what we're saying is that there is a queue. You put the head at 0 and the tail here. So to NQ is easy because you just put it at the tail, so that's O1. But to DQ, this is going to be ON. because when you remove the head, everything needs to shift up, right? So then an alternative to this is to configure it in a different way, such that the head is at the end, the tail is at the beginning. So in this case, if you want to DQ, it's simple, it's O1, because you just take it from the end. But now, if you want to NQ, so it means that you're going to push something to the 0, so everything needs to move up by 1, then that's going to be ON. So if you have the following configuration, NQ is O1, DQ is ON. For the following configuration, NQ is ON, DQ is O1. And this is kind of reasonable because when you have the head and the tail at different places, you got to pay the price some of the time. But is there a way for us to do this such that we can still do this in one time?
You mean like both?
Yeah. Now this is like a particular way of queuing up, right? So let's say all of you needs to present something, and so I put you in the queue. One way I can put you in a queue is to say that, alright, so we're gonna put a queue based on the number on your desk. So the head of the queue is gonna be a number 1. So if you're currently at the head of the queue, you make sure that you're a number 1. So then somebody's gonna be sitting there. Now when we DQ, then the guy comes up front to do the presentation. Then now the second guy have to take the place of the first one. And then there's gonna be a shift all the way, right? Now that process, because it requires shifting, is going to be ON. Now, but there's another way in which we can do that. So the other way to do that is actually just to remember who is currently the head. So for example, let's say you're the following arrangement where the head is at 0, the tail is at the end. So when you say you want to DQ, then we remove the element that is currently at the head. Then we just repoint the head to the next element, which is 1. So it means that we just keep a variable called the head, and the head is now going to point to 1. So say we remove it again, that's fine. Then the head will go to 2. And in the meantime, the tail, right, we just keep adding elements, right? And in that case, it's also O1. So you can have O1 to be NQ, O1 to be DQ. But there is a problem here. The problem is that over time, you're going to be wasting all these spaces because your head keeps moving down. These spaces are not actually used. So then although you pay O1 for NQ and DQ, at the end of the day, you actually pay the price in terms of space. And that is not optimal. So another way to do this is then to essentially induce a circular movement. So instead of adding a new element here or here, we ask the tail to go circulate back to fill this one. So now what this is going to do is that it's going to create a process in which the head will keep moving down, the tail is moving up. At some point, the tail may actually be ahead of the head. So this is what we call a circular queue. So you have a queue where the head is currently pointing here, the tail is currently pointing here, and as you DQ, the head is going to move this way. As you NQ, the tail is going to move this way, and the head is going to be chasing the tail all around and around. And in that case, you can reuse the space while still maintaining O1 complexity for both NQ and DQ.
If the tail is adding faster than the head,
If the tail is adding faster than the head, I mean at some point you don't have enough space, right? The whole space is full. Then you need to reform your queue, you need to create a bigger space. Because that problem also exists in this way, because in this case, if you allocate a specific space, at some point you're going to run out of space, then you need to create a bigger one. So meaning that at some point, if your circle is not big enough, you create a bigger circle to create a bigger capacity for the queue. the final concept here that we want to bring across, just one more, and then we will do a little bit of a class exercise. And the last concept is priority queue. So it's like a queue. The only difference is that we are going to decide not based on first come first serve. We're going to decide who leads the queue based on priority. Now examples of priority could be things like, for example, emergency room in a hospital. So if you go to a GP, you take a queue number because most people, they just have flu, they have cough and so on, it's not serious, so you can wait. When you go to the emergency room, it's not just based on the queue number, the nurse needs to assess how serious the condition is. Because if the condition is serious, then they may put you ahead of some other people, based on the priority. Now, for simplicity, here we're going to talk about smaller numbers having higher priority, whereas larger numbers having a bigger, lower priority. And here there are some examples of a priority queue. Now, there are different ways to implement priority queue. One way to do this is using a list, and you can keep it unsorted. If you keep it unsorted, when queue is easy, just put it anywhere. So it's O1. But to dequeue it, you need to go through the list to find out which one is the minimum value. So finding the minimum value is going to be O1, or ON, sorry. Or you can keep a sorted list. If you keep a sorted list, you always know where the minimum value is. So dequeue is O1. But to enqueue, you want to keep it sorted. But keeping it sorted is going to be ON. Because you need to figure out the place where to put it, and then you need to shift things to make room for the thing that you want to do. Then there's also implementation based on binary search tree. We are not going to cover it today because we're going to talk about binary search tree only next week. Now at this point of time, let's do a small class exercise because there are two concepts we want to bring across. Just now we talked about an implementation of a queue using a list, right? Now, the idea here is that we can define enqueue and dequeue in terms of abstraction. So meaning that I just know if I enqueue, it means I join the tail. If I dequeue, it means that I'm going to take something that is the head of the queue. But how you actually implement it is up to you. Whether it's a list, whether it's the head is at 0, whether the head is at the tail, and so on. So now what we're going to do is to try to see how do we implement it using a stack. Two stacks, in fact. You need two stacks.